Okay, hello everyone, and welcome to our second YEA Big Physics problem. And this is the video lecture for our second week. And our problem for this week is uh, a disk of uniform mass density, mass m and radius r, is at rest on the frictionless floor, and it can rotate, but the center can't move. And an ant of a much smaller mass moves in this circle as shown in the diagram, and it asks through what net angle does the disk rotate. Okay, so the first thing we're going to do here is set up a coordinate system. So this is the big disk, and let's make the center, the origin, 0, 0. Then this is the smaller circle that the ant traverses, and this is the y-axis, and this is the x-axis. Okay, so now let's say the ant has moved through a angle of theta to the vertical. Then what are the ant's coordinates now? Well, that's pretty easy to solve. You see that the center of this smaller circle is 0, r minus r. So then the coordinates of the ant now are just 0 plus the horizontal distance would be plus r r sine theta, and the vertical distance is r minus r plus r cosine theta. So these are the coordinates now, and the vector of the ant's position from the origin to this position now is r, and can be represented by this ordered pair. Okay, so then we have that the velocity vector v, well, it's at a constant, moving at a constant velocity v, so that's just v. And the in the horizontal direction, it would be cosine theta. And this is because if we look at this smaller circle here, and this is theta, this is v. And so now we get that this angle is theta. So the horizontal direction is obviously v cosine theta. And the vertical in the vertical component, we can see that it's going down. So that would be negative v sine theta. Okay. So now why do we write these vectors like that? Because what we want to find is the angle that the disk rotates. And that angle is equal to integral omega dt, right? Say the angle is phi. That's pretty easy to see. Now, what's omega? Well, omega is just L, the angular momentum, over I, the moment of inertia. Okay, so I we already know, and we'll deal with that later. But the thing here is that L is just equal to V cross R, which is pretty nice because now we can just take the cross product of these two vectors, and we know they're these two vectors as an ordered pair. So to find the cross product, this is something that you probably should know, is we take the determinant of this matrix, v cosine theta, negative v sine theta, and r sine theta, r minus r plus r cosine theta. And so then the angular momentum is just equal to, well, like the magnitude of the angular momentum is just equal to this determinant. And this isn't too hard to find. This is just v r cosine theta minus v r small r cosine theta plus v r cosine squared theta and minus this negative, so it becomes a plus VR sine squared theta. And this obviously just becomes VR. So we're left with VR plus uh VR plus V cosine theta times big R minus small r. So that's the angular momentum. And now we can look back at this integral. Integral of phi is equal to integral L over I times dt. And this is just equal to, well, this is exactly L. I made a small mistake. I forgot to multiply by M, but yeah. So just make sure you don't make that mistake. So it should be M times this. My bad. But yeah, the determinant part is more important, and you should be able to get that. So anyway, this is just equal to mv times br plus v cosine theta r minus r over, well, the moment of inertia. This is the moment of inertia of the disk, of course, and we know that is just equal to 1/2. And note, this is big M big R squared. And then times dt. Okay, so now we want to integrate this expression, but the only problem is that here we have dt when we really want d theta. This problem has an easy fix. We can just write that d theta over dt is equal to v over r, because d theta over dt is obviously just omega, which is v over r. So then dt is equal to r d theta over v. So now we can plug r d theta over v into this expression for the integral. And we get, this is integral 2m over mr squared times v times r plus cosine theta r minus r times r d theta over v, and this part cancels, the v cancels. So yeah, now it's pretty easy to integrate. This is just, we can look at the r and the cosine theta times r minus r separately. So this would be 2m and r squared over m r squared. And when we integrate, because that's like the constant part, and when we integrate d theta, it just becomes theta. Then plus 2m r over mr squared r minus r. That's the constant part of this second term involving cosine theta. And then when we integrate cosine theta d theta, that's obviously just sine theta. So sine theta. And it's not an indefinite integral. We're integrating from 0 to r to 2 pi. And this is because we can obviously see that the ant goes around the circle once, so theta goes from just 0 to 2 pi. So yeah, we have this integral now, and the nice thing is that sine 2 pi is equal to sine 0, so when we subtract them, this part just cancels, and all we're left with is integral of 2m r squared over big M big R squared theta from 0 to 2 pi. This is the answer we're looking for, pi. And obviously this is just equal to 2m r squared over m r squared times 2 pi, which is 4m over m times pi small r squared over big R squared. And so that's the answer we're looking for. And that is the angle that the total angle that the big disk rotates through. And so yeah, that is a useful problem, but like I like the problem. Like it's a hard problem, but like hopefully you understand how to do it now if you didn't already. And so yeah, well that's it for this week then. And well thank you for listening, and we'll see you next week for another problem. Thank you.